Math? You're giving me math?
Okay, hi.
Hi.
Ready to do some derivatives?
Yes, with my friend.
There's no better way. So speaking of friends, which friend are you?
Which friend do you think I am?
I'm going to go with Rachel.
I'm such a Rachel.
Yeah, what do you think I am?
You're a total Phoebe.
Yeah, I'm a Phoebe. I'm a Phoebe, and I think that is a great compliment.
This is so something that like Phoebe and Rachel would do together like on the weekends.
Yeah, I'm pretty sure it was an episode.
If it wasn't, it should be.
Yeah.
So let's practice some derivatives.
So no one told you life was gonna be this way.
That's fast math.
So let's recall some basics before we get started. So we have f and g both differentiable. How about the derivative of the sum or the difference of these functions? What is that?
Well, that would be the sum or difference of their derivatives. So we
That's
have
right.
f prime of x plus or minus g prime or of whatever the input variable is.
Perfect. Okay. Then I'm going to switch notations here and use that Leibniz notation. So
Right.
How about the derivative of a constant?
Derivative of a constant is 0.
Perfect.
One
Love
of our
that one.
favorites, yes.
How about we do some trig functions? What about the derivative of sine x?
That would be cosine x.
Perfect. And then while we're at it, how about the derivative of cosine x?
Negative sine x. Don't forget that negative.
Okay, and how about the derivative of tangent x?
Secant squared x.
Perfect. And how about the derivative of secant x? Because we're going to need that for this worksheet.
Sure, let's do that'd be secant x, tangent x. Ooh, and another one of my faves is the derivative of the natural log of x.
And the derivative of natural log x is 1 over x.
Right, and kind of related, the derivative of e to the x is e to the x.
Okay, so how about the power rule, which is a very powerful rule?
Good one, Phoebe.
Your job's a joke, you broke. Your love life's DOA.
I'm a doctor, Cliff, not a mathematician.
Okay, so this is a very powerful rule, and this says that the derivative of x to any power is that power, so that n, times x to the power minus 1. Yes.
So let's go ahead and use that in number 1. So we have this nice looking polynomial, and we're looking for the derivative of f. So f prime of x is equal to, so we bring that 4 down.
So we would get 17 times 4, so 68, x to the third.
Perfect.
The next one would be that negative 3 times bring the power down, so the 2, so negative 6, x to the first.
Okay, and then plus 3e squared.
Nope, mistake. Common mistake. Actually, we got Chandler on this one time, didn't we?
We totally got him. Yeah.
We got him.
That is not where we're going to use the power rule because e cubed is a constant, isn't it?
That's just a constant. So that's just some number, and the derivative of a constant with respect to x is 0.
Yep. Same with pi, right?
Right. Derivative of 3.14159 blah, blah, blah with respect to x is 0. Nice. So we've got our first derivative. We're going to do like 10 of them. This is how we hang on the weekends.
Yes, it is. Okay.
It's like you're always stuck in second gear. When it hasn't been.
We have 7 rats. So what if each of them has 7 rats, and then each of those has 7 rats?
Next one, the product rule. So again, we have f and g, these differentiable functions. So when we take the derivative of the product of f and g, go ahead and walk me through that.
Okay, so I like to call them, like f I'll call the first function, and g I'll call the second function. So the derivative of the product of the two functions is the first function. So f times the derivative of the second function plus the second function times the derivative of the first. So first times derivative of the second plus the second times derivative of the first.
Perfect, love it. So in this next example too, we want to identify the first and the second. So we have this polynomial would be the first, and the second would be tan f. The derivative of f, like you said, we have the first times the derivative of the second. The derivative of tangent x is secant squared x plus, then what?
The second, so tangent x, times the derivative of the first. So some power rule, 10x minus 3, and then plus 0, which we don't need to include.
Perfect. And there's not much to simplify here, so I think we can be done.
Yeah, on this one, if you try to do any like fancy algebra and clean it up, it's like a whole thing. Like you're gonna feel like you're always stuck in second gear.
It's like you're always stuck in second
All right.
gear. When it has
Next one, we have the quotient rule.
Quotient
So-
rule.
I'll be there for you when the rain starts.
Well, all I do there is try and divide 232 by 13.
All right, so I like to call these two functions involved the top and the bottom, which I think those are pretty obvious, but thank you for the clarity, Phoebe. And so the derivative of that quotient is the bottom function, so bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So you've got bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. We actually have spent some time in the cafe with your guitar with another way we could remember that.
That's right. I even
We
wrote
do.
a song about it.
You did, and it's
Yeah.
a glorious song.
It is. It goes like this. Low-D high minus high-D low, all over low low.
Low-D high minus high-D low, all over low low. So good.
Perfect.
Our single will be on Spotify next week.
Low-D high minus high-D low, all over low low. Low-D high minus high-D low, all over low low.
I mean, look, who was that?
They're your backup singers. Behind you, hun.
Oh,
From the top.
okay.
Low-D high minus high-D low, all over low low. Low-D high minus high-D low, all over low low.
Okay, so in this one, we're going to identify the top and the bottom. So f prime of theta, like you said, is the bottom times the derivative of the tops, and which is what?
The derivative of cosine theta is going to be negative sine theta. So bottom times
Perfect.
derivative of the top minus top.
The top times the derivative of the bottom. So the derivative of 1 minus sine theta is going to be negative cosine theta.
Right, derivative of 1 is 0. Derivative of negative sine theta is negative cosine theta. All over low, low.
Okay, so let's clarify here that the calculus is done, right?
This is the derivative. We're done with the calculus.
But then sometimes the question asks us to simplify the derivative.
Right, and last time it really didn't make sense. But this time there's some pretty stuff going on, isn't there?
There is, so I'm just gonna go ahead and distribute that sine through.
Right, so that negative sine theta is getting kicked to the 1 and to the other negative sine theta. Cool. Likewise, we've got that plus, ooh, I see something pretty on top. Look at, there's sine squared theta plus cosine squared theta, and trig identities will be there for you.
That's right.
They'll be there for you.
When the rain starts to fall.
When the rain starts to pour, but whatever, it's fine.
Oh.
When the rain starts to pour, the trig identities, they're
You
there.
know what?
How dare you? Okay, when the rain starts to pour, the trig identities will be there for you like they've been there before. That's why we need the for.
Oh, yeah.
The pour rhymes with the before. Okay.
Oh, okay.
Yeah.
Got it. Okay, can we do anything else?
Ooh, yes. There's some cancellation we can do because we have 1 minus sine theta on top and 2 factors of that on bottom. Beautiful.
All right, so we're just left with 1 over 1 minus sine theta to simplify that.
Nice. All done.
All right.
I'll be there for you, like I've been there before.
$350?
Down from 700, you're saving like 200 bucks.
Both logic and math are taking a serious hit today.
Okay, so next one, chain rule.
Chain rule. All right. We like
So-
to call it Chandler's chain rule because it's his faves.
It is his fave. So in this, we're looking at the derivative of a composition. So the derivative of f of g of x is equal to what?
All right. So I like to look at it as we've got like an inside function and an outside function. And sometimes there's more than one inside function.
Right. So the derivative of f of g of x is f prime of g of x times g prime of x. Okay, so for number 4, let's start with identifying that inside function. So like we wrote the rule, the g of x. And
Right.
number 4, our equivalent g of x would be what?
Well, we're taking the natural log of sine of x. So sine of x is our inside function. And
That's
then like
right.
the natural log of a quantity is playing the role of like our f of a quantity.
That's right. So when we take the derivative, we're starting off with taking the derivative of ln of a quantity, which is 1 over that quantity.
Right.
And at this point, we like to cross off.
Right. This
Right.
helps keep track. Like, oh,
Mhm.
we've taken the derivative of that part.
Mhm.
We've taken the derivative of natural log of a quantity, but we still have another step, don't we?
That's right. We need to take the derivative of sine x, which is what?
Our cosine x.
That's right.
Right, so you work your way in on this, and then you can cross off the sine x, and then you see, and you're always crossing off in the original function, like looking back at the original function, because then once you've worked your way all the way into your little x, now you know you're done.
That's right. And so this is the derivative once again, but we could look at this as cosine x over sine x, which once again, the trig identities are there for you.
They'll
And
be
what
there
is
for
that?
you.
They'll be there for you. And what is that equal to?
That is equal to cotangent x.
Perfect. Before we begin number 5 here, we like to write this as secant of 5 theta, all of that quantity squared.
Right, that helps us see the like outside function, and then there's like an inside function, and even another inside function here. So y prime, we notice the outside function is we have a quantity to the power of 2.
Right.
Power
we,
rule.
Yeah, we use power rule. So we have 2 times that quantity to the first power.
Right.
And then we like to cross off that 2. We've
Right.
taken care of that part.
Work your way in, always looking back at the original function, not looking at your work down in the derivative location.
That's right.
So now you have secant of a quantity.
Right. And the derivative of secant of a quantity is secant of that quantity times tangent of that quantity.
Right, and now you can cross off another little inside function. And this way we're looking back at the original, not looking back at the work we're doing. So we will know when to stop because we got to get all the way into the input variable. And that's theta. We're not there yet.
we're not there yet. We still have to take the derivative of 5 theta, which is just equal to 5. And now we're done.
Right.
This is 10 times secant squared 5 theta times tangent 5 theta.
Great. Beautiful.
Pretty. Next one.
You're still in bed at 10 and work again at 8.
That's math I can't even do.
Sometimes we combine more than one of the rules we just discussed.
That's right. So this is a whole smorgasbord of different rules.
Totally is. Okay, so let's look at it. We like to think of roots when we're taking derivatives, just like you're ready to write it, which is like a power, because that root is actually to the 1/2 power. Because we have
That's
the
right.
power rule. We don't have like a separate root rule. We don't need one. It's a power.
That's right. So it's a quantity raised to the 1/2. We have the derivative is 1/2 times that quantity raised to the negative 1/2, because that's 1 minus 1/2.
Right.
And now we're going to go ahead and cross off that 1/2 and work our way inside. And I'll let you take over here.
Right. So now we take the derivative of the inside. Derivative of 1 is 0.
Mm-hmm.
Plus, now the next part, there's a little product there. We've got
Mhm.
x and we've got e to the negative 2x. So that's a product of two functions of x. So we need a
Perfect.
product rule. So we've got the first times derivative of the second. So derivative of e to a power is e to that power. Using chain rule, that negative 2 will arise. Cool. Plus second, so e to the negative 2x times derivative of the first. The first function was just x, so that's just a 1. So that this is going to clean up pretty.
Perfect. Okay, so there's our derivative, and now let's just go ahead and simplify. So I'm seeing that we have this quantity raised to the negative 1/2. So we're going to go ahead and move that to the denominator.
Right. This one you definitely would want to simplify even if you weren't instructed to do so, because like you can just see there's a lot we can do here.
Right, and it's just ugly without.
Yeah, you don't want to be like still in bed at 10 when work began at 8.
You really know this song.
That's exactly what this would be like. That was like a perfect analogy to not simplifying. Lovely.
Right?
It's so, yes. And it looks so much prettier.
Way prettier.
You could even bring that e to the 2x downstairs if that was bothering you, the negative exponents. If
Oh
those,
yeah, why not?
And then it'll be even more pretty. And on top, ooh, yes, all over. Yeah, that 2. And then, yeah, e to the 2x downstairs. Ooh, it's so pretty. I'm like, ooh, hey, that derivative, how you doing?
How you doing?
How you doing? Mm-hmm. Gorgeous. She's gorgeous.
Okay, so with this one, we want to make our lives easier by remembering some logarithmic properties.
Totally, because there's like more than one way to approach this, but those logarithmic properties, which will be there for you.
Once again.
Yes. Make it a much easier problem.
That's right.
Okay, so another thing to notice just as we like take inventory of this function is this is a function of z, and a lot of people will get really spooked seeing the a's and the z's and the natural, like it looks overwhelming, but the only input variable is z. Anytime you see like the a squared, that's just like a constant. That's like 3 squared or whatever.
Right, okay, so now we go to take, actually we're not going to take the derivative yet. Okay, we're going to make this a little bit prettier before we do that. So g of z is equal to, yep, we can bring down that 1/2.
Right. This is a property of logarithms.
That's right.
We're not going to do like the power minus 1. Like a lot of people will be like, oh, you did a power rule, you're taking the derivative. No, not yet. This is a property of logarithms.
That's right.
And then when you have the log of a quotient, you can actually take the difference of the log of the top minus the log of the bottom.
Perfect. And that's all we can do with the logarithmic properties. So now we're ready to actually take the derivative.
Right. Common mistake. A lot of people look at those negatives and like the subtraction and addition inside the logarithms, and they try to make up their own logarithmic properties.
I can't with that one.
No.
I really can't.
No. It's a bad look.
It's a bad look. Don't do it.
No.
Okay. So now the derivative is 1/2, and the derivative of ln of a quantity is 1 over that quantity.
But if that quantity isn't just the z in this case, then you need some chain rule. And so the derivative of the inside of the natural log of the a squared, like we said, is just a constant, so that'd be 0, minus the derivative of z squared with respect to z is that negative, because it's negative in front of it, 2z to the 2 minus 1, which is 1.
Okay. And then minus 1/2, this is like same thing, right? We have 1 over a squared plus z squared times the derivative of the inside, which in this case is 2z.
Great.
Okay.
That's the calculus. The calculus is all there in green.
Perfect. So now we can go ahead and just do a little bit of simplification here.
Pretty algebra. Don't try to cancel any of those z's over subtraction or addition, you monsters.
Dear God, don't do that.
I know we're not supposed to judge as educators, but I'm just telling you, we're judging.
Okay, I'm just going to let you know right now that if you go like this, I judge you.
Yeah, and so does your teacher who says she doesn't or he doesn't. They are judging you, and they're talking about it with their friends.
And Rachel, I swear to God, if you cancel these, we are on a break.
We are not on a break.
We will be if you go ahead and cancel those Z's.
Fair enough.
Okay.
Okay, we are not on a break. Let's just put that in writing.
We're not. We can
mark it. We're not on a break.
We were on a break! We were on a break!
Your mother wondered there'd be days like these.
Each team will answer 10 questions. The first team to answer the most questions wins.
Okay, so now we're just going to do some together, just hanging out as friends, and hopefully you can practice on your own before we go ahead and go through these.
Yeah, just friends hanging out, doing derivatives. You might even pause it here, try it yourself. We'll do them.
Grab a friend.
Grab a friend, or we're your friends. And then at the end, let's compare our results.
Perfect.
Okay. The first one is definitely going to need some chain rule, some quotient rule, knowing your cosine. So all that good stuff, go for it.
I'll be there for you when the rain starts to pour. I'll be there for you like I've been there before. I'll be there for you 'cause you're there for me too. No one could ever know me. No one could ever see me. Seems you're the only one who knows what it's like to be me. Someone to face the day with, make it through all the rest with. Someone I'll always laugh with, even in the worst time that's with you. Yeah. It's like you're always stuck in second gear. When it hasn't been your day, your week, your month, or even your year. I'll be there for you when the rain starts to pour. I'll be there for you like I've been there before. I'll be there for you 'cause you're there for me too. I'll be there for you. I'll be there for you. I'll be there for you 'cause you're there for me too.
So much fun.
So fun.
Were there any questions?
All right, Rachel. Well, I love doing derivatives with you.
All right, so maybe we'll do some more derivatives down at Central Park next weekend.
Love it. Grab a friend, go get some coffee, and do some derivatives.
Okay, bye.
Bye.
Oh my God.
Lodi high minus Heidi low, all over low, low. Lodi high minus Heidi low, all over low, low.
I mean, look, who was that?
They're your backup singers. Behind you, hun.
Oh!
From the top.
Okay.
Lodi high minus Heidi low, all over low, low. Lodi high minus Heidi low, all